good morning to all of you. About 10 days back, when Professor Shom contacted me and said, Sundarajan, we are having this event. You have to come to the inaugural and give this a popular lecture. In fact, it would have been much easier for me to give a technical lecture on a specialized topic. But giving a popular lecture is difficult. When Professor Shom, who is like a bade bhaiya to me, when he says you have to come and give, the only option for me is to accept it. And it's, of course, on a serious note, I'm very happy to be part of this inaugural. In fact, training 10,000 teachers in the field of fluid mechanics through both synchronous and asynchronous mode of knowledge transfer is a very big effort, big initiative. And I'm sure that this will have an exponential kind of impact, explosive impact, really. That each teacher will be interacting with maybe a few thousand students in his career, and training 10,000 teachers means it's really a national mission. And the teachers who are going to be part of this effort are all leading experts in the area, and you have all the necessary machinery, tools, both visualization and other tools which are available. So I'm sure that this effort will go a long way in really providing impetus to fluid mechanics teaching in the country. I am very happy to be part of this effort, play a small part in this. And I thank the IIT Kharagpur administration, most of whom are my friends, for inviting me to this inaugural. Now going to the topic, if it has to be a popular lecture, then I was wondering what to talk on. Of course, fluid mechanics is such a subject which has confused me in many, many respects. I thought that I can talk about confounding fluid dynamics, CFD. I am known for my work on CFD, computational fluid dynamics, but this CFD is different, confounding fluid dynamics. That is the topic of today's lecture. Yeah. So can I go to the first slide, please? Yeah, like from here. Okay. So I just want to bring out an anecdote from the life of Professor Werner Heisenberg. Next one. So it was said that Heisenberg, who of course made a seminal contribution on quantum mechanics, everybody knows this Heisenberg's uncertainty principle, and he was initially supposed to work in the field of fluid mechanics on turbulence, and he made some efforts and then gave up and said, it's too difficult for me, no, I can't do this. And he changed over to quantum mechanics, and he this Heisenberg principle, of course, is thought of as a hallmark in quantum mechanics area. And after that success, he went back to turbulence again, he tried, again failed. So it seems that he once said that he had two questions to ask to God. One will be that why is general relativity so weird, so difficult to understand? The other one is how do you explain turbulence? And he said God would answer the first question but not the second. So turbulence still is something which is defying full understanding. A lot of efforts are going on. Of course, many advancements have taken place, but still, even with the latest, most powerful computer, still there are difficulties. And turbulence, of course, is not the only area. There are many others. In fact, we generally think that any small effect, small cause should have a small effect. So, for example, many great minds have worked on the area of fluid mechanics, none other than Sir Isaac Newton himself. And Newton, of course, discovered this law of viscosity. And today, almost all fluids are categorized as either Newtonian or non-Newtonian fluids. And after Newton, there were many others. So Newton, I think, worked on this about 350 years ago, in the 17th century. And after him, Leonhard Euler, he developed the mathematical formulation. Of course, he worked on continuum mechanics and mostly on solid mechanics. But he has also made a contribution in fluid mechanics, so-called equations for inviscid flow. Euler equations are credited to him. And after Euler, Claude Louis Navier, who was a French scientist, and George Stokes, an Irishman, and they both contributed to the development of equations for viscous fluids. And of course, the equations for viscous fluids are well known. But then, most of the scientists of that day, they said that for common fluids like water and air, viscosity is so small. I mean, if you look at it in terms of the Reynolds number, for any practical flow problem, so leaving out things like small dust particles settling down or water droplet falling, if you leave out those kind of very examples like that, but most other practical examples have very high Reynolds number, so which means viscous forces are negligible. Drop viscous forces, treat the fluid as ideal fluid, and try to predict things. When they predicted, reality was very different. In many cases, in fact, even for example, there is a famous so-called D'Alembert's paradox or something, where it says that a symmetric object like a sphere or cylinder, if there is a flow on it, there should not be any, drag should be very small, there should not be any lift. But in reality, you find that there is a significant drag, and there is also some oscillating lift. How do these things happen? And these kind of things were perplexing people quite a bit. Even as early as the beginning of 20th century, still these questions were continuing. And it is credited to Ludwig Prandtl. In fact, he was doing some experiments in some duct, and he found that the flow was separating. And he visualized it, and he thought that the layer close to the wall is the one that is giving problem, so he applied some suction. And once suction was applied, the flow behaved properly. So it was then clear that a thin boundary layer close to the wall was giving problem. And this thin boundary layer is because of the small viscosity of the air. So, in fact, we know that for any bluff object, even our automobiles and anything else, which are objects which are bluff, not streamline shaped, large drag comes because of the small viscosity. So, in fact, this gave birth to a new subject called as asymptotic theory, singular perturbation theory, where it was shown that small things need not have small effects, they can have large effects as well. So, if you take care of the boundary layer, it is possible to reduce the drag, it is possible to improve even fuel efficiency for cars and so on. So, just next, yeah. No, there is one before this. Okay, next one. One more perplexing question as I see is that we tend to think that if geometry is symmetric, the incoming flow is symmetric, then the outflow also should be symmetric, but that is not the case. Many times we find that it is asymmetric about the mid-plane, there are vortices being shed. So, symmetry of the geometry and symmetry of boundary conditions, etc., does not guarantee that the final solution will be symmetric. This is again another perplexing thing about fluid mechanics. And not only that, generally we tend to think that if you have a steady input, the solution will be steady. No, again, for example, this is what is shown here is uniform flow is approaching a cylinder, external flow over a cylinder. And although the incoming flow is steady, the outgoing flow may not be steady. It will be oscillating with specific time. So how do these things happen? Of course, experimentally we see this, and mathematics also explains in terms of instabilities and so on, but still, mind finds it difficult to accept as to why, when everything is symmetric, in the input is symmetric, why is output asymmetric? Why is it unsteady? And so on. Next. This is just a picture of flow over a sphere. As you increase the Reynolds number, flow is separating, and this is as I told you, the small viscosity playing a big role, that there is a big wake behind the sphere, and of course, if you still increase the Reynolds number, it will become unsteady. Though it may be symmetric, but it will be unsteady. And this unsteadiness can cause unsteadiness in drag, and of course, lift may not be there in this case. So, small effects, viscosity being very small, but still it can play a big role. Next. This is flow over a cylinder. At very low Reynolds number, we see steady flow, streamlines being steady. Then as you increase the Reynolds number, unsteadiness begins in the wake. And then finally, it swims up to the boundary layer of the cylinder itself, and then unsteadiness starts. We have what is called as a Harman vortex street, forming a kind of asymmetric flow pattern about the midplane. So, and if this continues, as you increase the Reynolds number even further, initially at least, this may be predictable, and you will have certain only few frequencies being present. It could even be a single frequency, and later on, few more frequencies coming into picture. But if you go further and further, the whole thing becomes random, unsteady, and random fluctuations come into picture. and that is in fact the hallmark of turbulence, that in a full grown, fully developed turbulence, you cannot determine everything. It will be more like a random kind of behavior, that random fluctuations in velocity, pressure, and so on will take place. Next. So you see, for example, this is from an experiment. One of our students had done that. So as the picture on the top is lower Reynolds number, you see larger eddies being present, and the one below is at a higher Reynolds number. Lot of small eddies are present, fine scales are present. So how do these things happen? And once it becomes turbulent, it is not, you can't predict it completely. Of course, now we have what is called as a direct numerical simulation. With very, very powerful computers, one can attempt it, but even then there are limitations, and you don't understand everything completely. Next one. So we see that the streamline patterns at some Reynolds number, you see oscillatory solution. These are some of the solutions that our students have. Okay, next one. And this is, in fact, the predictions that we did, we compared with results available in literature. And what we have shown, the literature results, most of them are experimental. Please see one important characteristic, that at low Reynolds numbers, the scatter is very high in experimental work. Not in theory. In experimental work, there is a lot of scatter. Why would that happen? The reason is that even flow separation and vortex shading, etc., they are all dependent on some kind of small, let's say any surface which is machined will have asperities. Those asperities will determine at what Reynolds number flow separation will take place, and at what Reynolds number unsteadiness will occur, and so on. So from one experiment to another experiment, the roughness could be slightly different, and these things matter a lot. So what it shows is that small things can have large effects. So we come back to the theme again. Next. This is Struhal number. Struhal number is nothing but if you non-dimensionalize the oscillation frequency, then you form a non-dimensional number known as Struhal number, and predictions are reasonably okay. But even here, at lower Reynolds number, the scatter is somewhat higher. Next. And we did some work with tandem cylinders, and let's say two cylinders, one placed behind the other, or one placed by the side of the other. And a lot of interesting phenomena took place. Depending upon the distance between the cylinders, you can suppress vortex shading completely, or vortex shading may exist if you separate them further apart. If they are placed side by side, you can have coupling between the vortex shading. You can have what is called as in-phase coupling or out-of-phase coupling. So a lot of such interesting phenomena take place. That is, when two cylinders are there, they can shed vortices in tandem, synchronously, or they can do it asynchronously, out of phase. So in-phase, out-of-phase phenomena are possible when there are multiple objects like this. Next one. So that's what it says, that vortex shading can be suppressed, or it can be in phase and out of phase shading, and so on. Next one. So this is two cylinders, one behind the other. For this aspect ratio, for this spacing of 3, you find that vortex shading completely suppressed in the space between the cylinders, but behind the rear cylinder, obviously there is still wake oscillation. Next one. And here, of course, if the spacing is increased, this is about L by D of 7, you see that there is vortex shading behind the first cylinder also. So a lot of interesting phenomena take place. Next one. Yeah, this is about we compared with literature data. Next one. Next one. Yeah. And oscillations can be seen, especially at higher separations. Next one. Yeah, next one, please. This you see, for example, two square cylinders placed side by side, and here, in fact, in this separation, sidewise separation, we see in phase shading. More or less, the top and bottom cylinders are shading in phase, whereas the next slide, you see them out of phase. We have increased the spacing, so they are sort of shading in out of phase. So the in phase, out of phase shading is possible depending on the spacing. If you think of what applications can these have, if you think of high speed jets, you know that high speed jets, especially supersonic jets, make a lot of noise because shocks are present. and those shock cells emanate large amount of acoustic radiation, and noises can be several, maybe more 120, 130 dB or 150 dB and so on, which can be injurious to the hearing itself. So one way of reducing the noise is to put another jet. So if there are two jets, and especially for certain spacings, the noise can cancel off. Noise from one can cancel off the other if you make them out of phase. So which means that two jets will make less noise than one jet. So it is possible, you can cancel the noise that way. Next. Of course, the earlier examples that we showed were external flows. Even in internal flows, some interesting phenomena take place. So this is flow past a sudden expansion in a duct. Next one. Just the geometry is shown, where of course we have allowed some entrainment of air in the bottom picture. The one above, it does not have any, there is only one jet coming into a sudden expansion. And this gives rise to what is known as a Wanda effect. Wanda effect means a jet which is coming into sudden expansion can attach itself to the top wall or to the bottom wall, and both modes are possible. And at a particular time, which way will it go? Will it go to the top wall and attach, or bottom wall? It's a matter of, maybe it's a random phenomenon, or as I said, smallest disturbances can lead one way or the other. But mathematically, both modes are equally probable. Next one. You can go to the next one. Yeah. Next one. So you see here, so we have predicted this jet expansion in a duct at different aspect ratios for the same Reynolds number of 200, and the aspect ratio alone has been varied. We see here that we can attach at very low aspect ratios. It is going as a symmetric jet, spreading as a symmetric jet. As you go to higher aspect ratios, it is of course attaching it to one wall or the other. Both, in fact, we have seen that for the same aspect ratio, for same Reynolds number, sometimes the jet attaches it to the top wall, sometimes to the bottom wall. Experiment also has shown this. Theory also shows that either way is possible. Okay? It depends upon initial conditions that you start with. Next one. This is at still higher aspect ratios and higher Reynolds numbers. The jet is oscillating like a flag. All right, it's a transient instability, and it is not attaching itself to any one wall permanently, but just going like a flag. And this sort of oscillation is also possible. And something which has really perplexed me in this, we have shown for internal flow, we also shown for external flow, that if you think of flow over a cylinder, for example, initially it is symmetric flow. Then, of course, rotation, the separation, flow separation takes place, again, which is symmetric, followed by unsteady shedding, which is asymmetric. Similar kind of thing we have seen here also for internal flow. Initially, jet is spreading symmetrically. Then it starts attaching itself at steady state to the top wall or to the bottom wall. Then at still higher Reynolds numbers, it starts oscillating as a function of time. So there seems to be a hierarchy of these kind of instabilities. First, a symmetric steady one comes in, and then the transient one comes in, and so on. And in fact, flow over a cylinder, there are many, many other things. In fact, my friend, Professor Sanjay Mittal from IIT Kanpur has looked at it, this vortex shedding behind a cylinder in great detail. And he finds that there are many, many transitions, and sometimes from 2D it becomes 3D, and so on. Three-dimensional effects come into picture, and these are also a kind of, the forward and the reverse. If you increase the Reynolds number or decrease the Reynolds number, it doesn't follow the same path. So there's some kind of hysteresis. So all kinds of intricacies are there. And of course, why do these things happen? Again, reasons are not known. I mean, not in so much detail. Of course, mathematics will tell you that this is possible, but then mind finds it very difficult to accept. In fact, that was the reason why I mentioned this confounding fluid mechanics, fluid dynamics. There are many, many things which are still perplexing. Next one. And we have seen that if you allow entrainment to take place in the duct flow, that changes the picture completely. In fact, even at high Reynolds numbers, it tends to be steady, and oscillations do come in, slow oscillations come in at very high aspect ratios. So like a flag, it will be oscillating. So like this, with and without entrainment, the picture is very different. Now, again, one may ask the question, where do these things have application? Many times in aircraft combustors and so on. So from a small duct, the combustor may be a sudden expansion, and there will be recirculation, corners, there will be recirculation patterns, and they can be steady, unsteady, and that can have a big effect on the stability of flame inside the combustor. So this just shows the Reynolds number, critical Reynolds number as a function of aspect ratio for the steady case and for the transient one, for entraining flow, for non-entraining flow, etc. So sudden expansion across a duct also has a lot of, internal flow also has a lot of such interesting features. Next one. This is an instability. I think just click on this movie. Okay, doesn't matter. Go to the next one. Next, yeah. So of course, where there are density differences between fluids, finger-like growth is possible. So this is numerical prediction. We are compared with somebody else's prediction. So these involve multi-phase flow modeling. Next one. So the growth of a finger-like structure. Next one. This is a very interesting effect. In fact, the reason has been found only recently from micro-nano technology. In fact, the great philosopher Adi Shankara, he has said something, in philosophy, of course. He says, "Nalini dala gata jalam atitaralam, tatu jivitam atishaya chapalam." That is, water that has fallen on lotus leaf, how unstable it is. Life is also very uncertain. That's what he says. And both in Hindu and Buddhist scriptures, the lotus leaf has been compared as a symbol of purity, because although it is in dirty water, but the water doesn't soak it. It's clean of dirt as well as water. All right, and also has a sense of detachment from samsara, etc. So it has been quoted quite a bit in the scriptures. And if you look at the reason why this is happening, that on lotus leaf there are a lot of micro scale projections, and on the top of them nanoscale projections. So these nanoscale projections, for example, in the bottom picture that you see here, so there will be a layer of air which is trapped between these nanoscale projections, and that functions like a cushion. So because of which the contact angle can be greater than 150 degrees, of the order of 150 degrees or more, in which case it doesn't wet the surface. So non-wettability is a characteristic of lotus leaf. And so water or even honey for that matter, which is placed, will not wet at all. And this, now we can produce surfaces having these projections at micro nano scale. It is possible to produce them. And so they will be highly non-wettable. So for example, gloves that we are using for dealing with some dirt, etc. If you have this kind of stuff, it won't wet at all. The dirt will not stick. So it is possible to use it for several applications like this, and even possible to generate such surfaces with micro and nano scale projection. Next one. Yeah, this is the Rayleigh-Bénard convection. Of course, if there is some temperature differential between, let's say, in a layer, that can create natural convection, especially if the Rayleigh number characterizing the problem is greater than the critical value. Next one. We have looked at two-layer Rayleigh-Bénard convection. And so there are two fluids and there is a temperature differential. And with this, a lot of interesting phenomena take place. We have steady convection in both layers, or convection in one layer driving the other. That is, bottom layer alone can have the convection. Other one can be a mechanically coupled one, not thermally. So that is, one layer has already reached the critical state. So it is having natural convection. The other one has not reached the critical state, but still mechanically it can have a convection inside that layer. Or this can have oscillatory kind of convection as well, where convection in bottom layer, then it becomes top, then again between bottom, again top, etc. Stationary or standing wave type of convection is possible. Then you can also have what is called traveling wave convection. That is, the convective rolls will be moving up and down. So all kinds of phenomena have been seen between two layers depending on the temperature differential, the properties of these layers, the density ratio, the viscosity ratio, the conductivity ratio, etc. Depending on this, many things are possible. In fact, the diagrams that are shown there, different modes, first mode, second mode, etc. we have shown. And in fact, to solve such stability problems, you have to go to very accurate methods, like spectral method has to be used to really resolve them very well. And we find that certain, for example, if you take the middle graph on the left, the left side shows bottom layer being the driving layer, and the right shows the top layer as a driving layer. And in between, it's an oscillatory regime where top and bottom can alternately drive each other. And it can either be a standing wave mode or a traveling wave mode. Next. They show some of the pictures here. Yeah. So one being dominant over the other. I think here the top layer is the dominant one. Next one. Here they are almost equal, and this is, I think, standing wave mode. Yeah, next one. Next one. So a lot of quickly we can go. Next one. Yeah, you see, for example, the standing wave pattern is possible. Here, as a function of time, we have shown some of the lines as solid lines, some of the lines as dotted lines. So the solid and dotted lines represent the sense of convection, either clockwise or anti-clockwise. This clockwise, anti-clockwise is switching as a function of time. So a standing wave pattern is possible, and a traveling wave pattern is also possible. Yeah. I come to the end of the lecture. So I have shared with you some of the confusions that I have had, that fluid mechanics abounds in such kind of things, that a small cause need not have a small effect, can have a large effect. Then a steady input, symmetric geometry, solution need not be symmetric. So it may be asymmetric, it may be vortex shading, it may be a transient one, and so on. And even example of lotus leaf, that small projections there make the phenomena so different that water does not even stick, or dirt does not even stick. So it is a very exciting subject. You have great experts who are going to interact with you over the next few months, and I'm sure that this will be a great success. Let me wish the effort all success. Thank you. Is there any questions? I would be more than happy to answer. I guess I have confused everybody. Thank you.